Hey guys, so in today's lecture, we are going to discuss energy from tides. So, as the chapter proceeds of ocean energy, we have seen how we can get energy from the temperature difference, the thermal energy which is stored in the ocean by absorbing the radiation of the sun. So, now we will see how we can generate energy from the tides, that is from the tides of the ocean. So first we will see the principle, and then we will see various systems through which we can generate the energy. So first we will understand why tides are caused. So tides are caused by the combination of attraction of sun and moon on the waters of the revolving globe, because the globe is revolving and its attraction both of combination of sun and moon, the tides are caused. So once ocean tides are, we can say ocean tides are periodic rise and fall of ocean water level occurring twice in each lunar day. Rise and fall of water occurring twice each lunar day. So every day there will be a rise and a fall of water. So the tides are periodic vertical rise and fall of ocean water. The tidal rise and fall of water is accompanied by periodic horizontal to horizontal to and fro, means forward and backward motion of water called tidal currents. These are called tidal currents. This is called tidal currents. So due to this rise and fall, there is a to and fro motion, that is tidal current. The tidal current flow in horizontal direction have kinetic energy. This tidal current have kinetic energy. So this energy is called tidal current energy. So this is called tidal current energy. So the period between consecutive high tides. So the period between consecutive high tides is 12.5 hours. That is, if there is a high tide, then after 12.5 hours, then again we will have a high tide. The speed of the tidal currents is in the range of, so the speed is in the range of 1.8 kilometer per hour to 18 kilometer per hour. So these are the speeds of the tidal currents in which they are moving forward to and fro. Now we will see a tidal range. Suppose let's draw a graph. Suppose y-axis, x-axis. Suppose on the y-axis we have water level. This is water level. So this is the base we are selecting as water level, and above it there will be high tide and below it there will be low tide. So, and this is, suppose on the x-axis we are having a time period. It is a lunar day. So lunar day exists of a 24 hour and 50 minutes. So lunar day is 24 hour and 50 minutes. That is moon day. So there will be a high tide, then low tide. It will go according to the sine curve, high tide and low tide. So this is one tidal cycle. This is one tidal cycle, and this is the second tidal cycle. So in a full lunar day, we will have a two complete cycle tidals, a complete tidal cycle. So the upper point we will call it as A, and the lower point we will call it as B. The rise and fall of the water follows a sinusoidal curve. It is it follows a sine curve. It is called a sinusoidal curve. The point A, this is indicating high tide, and point B, this is indicating low tide. And the tidal range R is the difference between consecutive high tide and low tide water levels. So R is equal to high tide level, that is A, minus B. So this is R. This is R. So that is A minus B. So now we will see. So as we have plotted the graph of tidal level versus a whole lunar day, that is 24 hours and 51 minutes, 50 minutes. So now we have plot a lunar month graph, that is for whole 29 days and 51 that is hours. So 29.51 days, so 29 days and 12 hours around. So what we have seen, so in full lunar month we have various. First is a new moon, then the first quarter, then there is a full moon, then there is a third quarter, and then again it is a full moon. So lunar consists of 24 hours and 50 minutes, and in one lunar day there are two low tides and two high tides. The effect is maximum when Earth, Moon, and the Sun are in one line. Since the Moon is nearer to the Earth than the Sun, hence Moon has greater contribution in formation of the tides. The surface of the Earth facing. So, if we draw the Sun Moon system, so suppose Sun is in the middle, and suppose uh, we are drawing suppose four phases. So 1, 2, 3, 4. So this is Earth, suppose Earth, 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 and suppose this is Moon in one direction. Suppose Moon is in this direction, Moon. So we are considering all the four cases. So Moon, and suppose Moon. So here there is the pull of the Sun, and this is the pull of the Moon. Similarly, here there is the pull of the Sun and Moon both, and here is the pull of the Sun, and here is the pull of the Moon, and here is the pull of the Sun, and here is the pull of the Moon. So when the Sun, Moon, and Earth are in this same direction, that is they are in all the same direction, in one line. So hence the moon has greater contribution in formation of tides. The surface of the earth facing the moon experiences greater force of attraction than the surface away from the moon. So that is this surface. The surface which is facing the moon will have greater effect than the other surface which is not facing. So the force of attraction of the moon is 2.6 times than that of sun. So the force of attraction of moon is 4.6 times that of sun. So the force of attraction causes acceleration of water and earth towards the moon. So the water is getting accelerated the uh, towards the earth or towards the moon. The mass of water shifts towards the moon. Thus, ocean water on the moon side experiences high tide, and on the other side experiences low tide. So here it will experience high tide, and here it will experience low tide. Such daily tides are called the diurnal tides. Diurnal, urnal, diurnal tides. The diurnal tides include two low tides and two high tides for one rotation of moon around the earth. Now during full or new moon, when the sun, moon and earth are in a line, the gravitational forces of the sun, moon are enhanced and the tidal range is large, and the tidal range is maximum on the full moon and new moon, and such tides are known as spring tides. And such tides are known as spring tides. So here as you can see, on the new moon, on the full moon and again on the new moon, the tides are high. These are known as spring tides, and the tidal range is minimum on the first quarter. The tidal range is minimum on the first quarter and the third quarter of the moons, and such tides are known as these tides are known as neap tides. NEAP. So the tidal power is proportional. So tidal power is proportional to the square of tidal range. To the square of tidal range. Hence, sites having more average tidal range, about 5 meter or more, are preferable for tidal power plant. So, for tidal range greater than 5 meter, are preferred for tidal power plant. So, this is the concept of tidal energy. So, how tides and tidal energy works. Now, now we will estimate the tidal power in a single basis system. So how much power it can generate, this tidal power in a single basis system. So I will draw a diagram. So for single basis system, suppose we are constructing a dam. So this is suppose a dam, and this is the area A. This is the basin. This is turbine. And suppose this is the height from the basin H, and suppose this is the tide range. So this is suppose high tide level, and suppose this is the low tide level. Now we will define some uh, variables, that is suppose this R is the tide range, R is the tide range, H is intermediate depth, and DH, this is DH is small change in head, DH is small change in head. A is surface area of water, M is equal to mass flow of water through turbine, rho is density of water. So now if we are considering an elemental thickness of water dH at a height h, okay, so we want to find for whole tide range. So the work done by the water, work done by the water dW will be equal to, that is dm into g into h. So but what is dm? Mass, small mass, so mass is equal to, that is density into volume, that is minus rho a into dh. So if we apply this mass in the formula of work, so the dW will be equal to minus rho a g h dh. Now the total theoretical work during a full emptying is obtained by integrating the equation. So we will integrate this equation, W will be equal to 0 to R dW, so which is equal to 0 to R minus rho a g h dh. So if we integrate, we will get rho a g h square by 2, and the limits are from 0 to R. So our work done will be rho a g R square by 2. So this is our work done. So it is evident that the work potential is proportional to the square of tidal range, that is R. So the power is the rating of doing work. The average theoretical power delivered by the water is W, and divided by the time it takes each period to repeat itself. So the average power will be, so power is work done upon time. So there is work done upon time. So the tidal cycle between high tide and low tide is around 6 hours and 12.5 minutes. So which is equal to, t will be equal to 12.5, so t will be equal to 6 hour and 12.5 minutes. So if we want to find in seconds, if we count in seconds, it will be 6 into 3600 plus 12.5 into 60. So t will be equal to 22350 second. So p average will be equal to w upon t, that is rho g a r square upon 2 into 22350 22350. So assuming, if we are assuming the water density rho is equal to 1025 kg per meter cube, then P average upon area A, P upon A will be equal to 1 by 2 into 1025 into 9.81 upon 22350 into r square. So P average upon area A will be equal to 0.225 r square watts. So the P average, that is power, directly depends on r square, that is 0.225 r square, and this is the constant 0.225. So we'll see few examples using these equations also that were asked in the GTU, and this is the estimation of tidal power which we can gain from the tides. So I hope you understood these equations, and you will see uh, other systems also, that is this was a single basin system, and we'll see other double cycle ebb and tide cycle systems. So thank you very much.